Hi everyone, my name is Pia and today I'll be presenting the research that I conducted this summer in the Artur lab during the Robotics Institute's summer school. We worked on evaluating vital sign predictions from incomplete patient data using Bayesian networks. Mass casualty incidents like natural disasters present unique challenges to first responders. Traditional vital sign assessments can become impractical when dealing with large numbers of casualties or hazardous environments due to danger to medical personnel and resource constraints. Autonomous systems can help responders in mass casualty incidents by finding and assessing victims' health, enabling emergency responders to care more for patients directly. A key challenge in this is how we can provide reliable medical assessments when we have incomplete, noisy data from autonomous systems. Although existing models can predict single health indicators, making a full assessment remains difficult. In this research, we assess Bayesian networks as a method to aggregate multifaceted knowledge when faced with missing information and uncertainty in the framework of a simulated mass casualty incident in a competition setting. The emergency response system that our Bayesian network integrates into is developed for a competitive environment and composed of unmanned ground and aerial vehicles that collect data through RBG cameras and thermal imaging. This data is then analyzed and processed by machine learning models on and off-board the robots in order to predict vital signs and locations individually. The Bayesian network then receives these potentially incomplete reports and fills in missing vital signs, providing complete medical assessments to users in real time. In order to be able to make predictions from incomplete data, we need a way to make inferences from it. We make use of Bayes' theorem in the form of Bayesian networks, which are probabilistic models that encode dependencies between nodes. Each node in our Bayesian network represents a vital sign that we are predicting. Unlike isolated machine learning models, a Bayesian network can consider clinical dependencies between vital signs in its structure and probabilistic makeup. For example, it can be modeled that the presence of strong bleeding or severe hemorrhage relates to other physical traumas and impacts in turn motor alertness. Our network was designed entirely from expert medical opinion, making it interpretable and requiring no large datasets for training. On the right here we can see an example for making a Bayesian inference. For example, we know about one person on the field that they have a torso injury, a head injury, and that their eyes are closed. Also, they are moving abnormally. And then we wonder what other states could their vital signs be in. For example, how likely is it that they are also unresponsive verbally or have some other physical traumas? So we can probabilistically infer from the given information in our network that the way we have modeled it, it is rather unlikely that they have other physical traumas present, but more likely that they are not verbally alert and also have some severe hemorrhage present. We evaluated the performance of our Bayesian network using 3 simulated mass casualty incident datasets reflecting realistic operational conditions and different injury patterns. We constructed partial noisy evidence by hiding 1 to 9 health indicators per case and injecting label noise in the range from 0 to 100% in 10% steps. A random classifier picking from valid labels was chosen as a baseline. The performance was measured in the scope of accuracy and score. For the score, each of the health indicators have been weighted in order to give more focus to health indicators that are very critical, for example, the presence of severe hemorrhage or respiratory distress. Our results show that for our analyzed dataset, the Bayesian networks outperforms random classification for most vital signs. Interestingly, some variables like respiratory distress actually improve with more missing data. This happens when the network's prior probabilities align well with the frequent conditions in the dataset. However, variables like motor and verbal alertness consistently underperformed, indicating areas for improvement in our priors. Our systems maintain a strong performance compared to random classification even under high noisy input, crucial for our development where our sensor limitations and environmental obstacles cause measurement uncertainty. This figure shows a representative result with 5 out of 9 variables hidden and 50% noise present. This means that 4 health indicator labels were used as an input to our Bayesian networks and they were only 50% accurate. The main advantage of our developed Bayesian network are fast inference speed and interpretable reasoning that medical professionals can verify. However, our performance depends on how well expert priors align with the actual label distribution in the casualty dataset. Here we can see the performance of our Bayesian networks on two different datasets, and when you, for example, compare our prediction accuracy for severe hemorrhage, you can see a difference with growing occlusion for both datasets, because the stronger the occlusion, the more importance the priors have compared to the evidence that is presented. If the priors then don't align very well with the present distribution, the performance suffers for growing occlusion. To improve this generalizability, we could, for example, introduce knowledge about scenario-specific injury distributions from domain expert or existing datasets. If we instead consider the score for a measure instead of the accuracy, we can still see a difference between the critically weighed health indicators, but less so between the non-critically weighed indicators. Still, the area where we need to improve on is clear in motor and verbal alertness. Our research demonstrates that expert-designed Bayesian networks can achieve competitive performance for predicting vital signs and automated emergency response, while providing an interpretability framework. In order to be integrated into a multimodal prediction system that can be applied to real life, we still need to improve our Bayesian networks' generalizability to different datasets, especially real-world data. Future work should compare our system against non-simulated data along with measures beyond accuracy. Also plan to extend our framework to handle continuous physiological measurements such as heart rate and respiratory rate, and confidence measures from other system components. I would like to thank my mentors and everyone in the Artur lab for their support with my research, and everyone involved with the RISC program this year to make this wonderful summer happen. Also thank you for giving my presentation a listen. If you should have any questions, please feel free to contact me or check out the RISC website.